Hello, my students. Yes, I'm here. I made it to work with the help of a big, fluffy bear's coat and other magic. Unfortunately, I still have to give you an assignment. It's mostly just this video lecture, so watch this. Uh, Hopefully, we'll be open by Wednesday so we can proceed with lab. If not, we'll have to push things back. Well, it can be done. We'll make it work one way or another, but I prefer not to have to do that, so we'll see what we can see. But with that in mind, I'm going to go ahead and start. I'm not going to give you a full lecture, but enough to get things started so we're not too far behind. This chapter, this first real organic chapter, not organic spectroscopy, is about radical reactions. Reactions that involve radical chemistry. So, one thing to note about radicals is that they are very highly reactive intermediates. They will never contain an octet. So, they will keep reacting. We cannot capture these intermediates. I mean, we can capture them in the sense that in a vacuum you can maybe separate some of these, but you cannot. You can capture them in the fact of when they bind to things, become less of a radical, but they usually decompose rather fast. These reactions are very fast style reactions. Think of them having very low activation energy barriers. Now, trigonal planar, the one thing to note about them is they will have trigonal planar electron geometries. They will essentially be sp2 hybridized. So meaning you're going to have flat 3 bonds, 3 sigma bonds, and a p orbital with a radical in it. Now, because the p orbital has a radical in it, it's much like reactions with lone pairs, like this, where depending on what side of the lobe of this p orbital reacts, you could get different stereochemistry. And there's usually not a difference between attack from the top or attack from the bottom. Please note, when we draw these guys, when we have to draw mechanisms of these guys, they will involve a single half arrow. And it will often need a second half arrow coming together. So sometimes you'll see them colliding in empty space. So real quick, let's show something like that. Let's go to the doc cam. While normal reactions, like if I had a CH3 anion, now I know this is not very stable, attacking, say, HBr, you would show it like this. Double arrow, double arrow. The double arrow suggesting 2 electrons are moving. So we produce CH4 and Br minus. When we have radicals, so like a CH3 dot, let's do the same reaction. We're going to have we're going to see a single arrow, half of that coming together, and half of that going there. So the byproduct still is going to be methane in this case, but that single arrow now suggests that bromine, it's exactly that. It's bromine radical rather than bromide ion. So, and for example, normally if I was to combine a anion with a cation, you would just draw it like that. And you would have, of course, CH3 bonded with CH3. But in the case of a radical, two radicals coming together, you would draw the two half arrows meeting in space. And you would still have the same product in this case. Two half arrows are needed to show one new bond being made. However, unless two radicals are meeting, we need three half arrows. Three half arrows. So just something to be aware of. But okay, let's look at this. So now, radical stability. And in terms of radical stability, it follows the same trends of carbocation stability. That methyl radicals are least stable. That primary radicals are second most unstable. Secondary is again more stable, and tertiary is the highest level of stability we can have. Has to do with we're missing an electron, and so we want something that can donate electron density that can help stabilize us. So alkyl groups are more polarizable, more capable of donating electron density, so they can stabilize this missing octet. But unlike cations, radicals will not rearrange to form a more stable radical. So we don't have to worry about, oh, there's a secondary radical, it's going to pop off and swap to a tertiary radical. We're not going to see any shifts. So whatever we start with, it's going to stay. Now, how do radicals form? Typically, if a bond is weak enough, they will form with either the input of heat or the input of light. Light, seen as H nu, is one of the most common initiators. But they can also form by using certain radical initiators, such as peroxides. Peroxides are highly oxidizing. We've seen them before, and that they can sometimes add an epoxide to a double bond. But peroxides are also very unstable in light, and so we can use light to cleave the peroxide linkage and to form a radical initiator of RO dot. These radicals are then capable of cleaving sigma bonds or converting nearby pi bonds into sigma bonds. But usually, as long as there's only one radical in solution, you're going to always generate a new radical. They always form a new radical. They often need radicals to initiate a chain reaction. But once they go very fast, and they go for a while. So a simple reaction. A sigma bond cleavage will occur with nonpolar alkanes. So it doesn't matter that the fact that it's nonpolar, and usually nonpolar alkanes do not react. You have a radical, it can pull off this. So chloride can pull off a CH bond and create a radical. Radicals will not react with polar or ionic electrophiles or nucleophiles, so we won't see a lot of reaction in our normal functional groups. So things that have a really strong attachment to their lone pairs. So here's an example of a radical reacting with a pi bond. So the radical from the chloride comes together with one of the electrons in the pi cloud and thus creates a new sigma bond and so we have the other radical staying in that p orbital. So it created a new radical though. Radical reactions will make a radical that can keep reacting, and so they're going to keep forming new radicals. And so we have a lot of different things we can do, depending on what we have mixed in there. One of the key ways to stop a radical reaction has to do when two radicals meet. They will form a stable bond without creating a new radical. So, for example, if I have chlorine radicals, while we saw that chlorine radical could steal a hydrogen or combine with a pi bond, if we have too many chlorine radicals, they can bump into each other and stop reacting. Or if I've created enough chlorine radicals to react with the alkane radicals, we can just form a bond without generating a new radical. Also, things like oxygen and other antioxidants can act as radical inhibitors or scavengers. They can bind, and these radical inhibitors, despite having a radical in there, are stable enough that it will stop the chain reaction. So that's kind of why oxygen is so important. That's why we take many antioxidants, because they scavenge the radicals that can be damaging. So one of the first reactions we will look at is halogenation of alkanes. It's one of the few reactions that's capable of interacting with alkanes, because normally alkanes are non-reactive. You need a functional group on there to get things going. It's really hard to just react with an alkane. I mean, alkanes are the strongest bases, so you can't very easily pull off a hydrogen. They don't really have a preferential attack spot, so it's really hard to modify alkanes. So the basic idea is we mix some sort of halogen with an initiator, either heat, which is our delta sign, light, our H nu, or some radical initiator like peroxide. And the net effect, when all is said and done, is we form a monohalogenated alkane and an acid. Now, this is going to be a common thing we're going to see in this semester, is largely we will focus on reactions of chlorides and bromides, chlorines and bromines. There will be ways to react with the other halogens, but oftentimes fluorine is too reactive, and so we can't control it, sometimes explosively. Iodine will react too slowly, and so it won't go fast enough. You won't get much of a product, but chlorine and bromine are in the happy zone. So if excess halogen is added, you can get complete halogenation to occur. So it's not that it necessarily will stop at a mono halogenated. It's just if you have enough, like stoichiometric amounts, say in this case, if I just keep reading, oftentimes excess or stoichiometric amounts of hydrocarbon is added. That's to make sure we only get monohalogenation. So the idea that it's okay if some of our alkane is unreactive. We will just separate that alkane out. we want to make sure we have just a single substituted alkane. And then remember, we can do things like SN reactions or beta elimination reactions or all sorts of various reactions on a monohalogenated alkane. So now the mechanism. We'll go a little bit into this and then we'll probably stop. So the mechanism of halogenation, it can be broken down into 3 basic steps. Almost all of our mechanisms will be broken down into 3 steps. Step 1 is always initiation. We have to make a radical. You can't store a radical, so we have to make the radical first. You want to make that in situ. You want to make that in solution so that it will immediately start reacting. The propagation step is the step that keeps the reaction going. And then termination stops the reaction. So this is a chain reaction. Remember, each step, we're going to spend a lot of time in the propagation step. So it's going to form a radical. We only need to make a little bit, catalytic amounts, and then the propagation will proceed until all of our chlorine gets used up, or until all the radicals get used up. So the majority of the reaction time is spent in the propagation, so it's a chain. So initiation is the rate determining step. It's where we only want a catalytic amount of initiator in order to minimize multiple halogenations. If you have a bunch of halogens hanging around, you're going to get some termination steps, and there's a chance you might have enough that the halogen's going to react multiple times with the same alkane. But so the rate determining step is we split one of our halogens into 2 radicals. So you notice the arrow goes to one radical, the half arrow goes to the other halogen. So we have 2 equivalents of the halogens. Now the propagation is then repeated multiple times. It's a 2-step propagation, but it gets us back to our starting material. This regenerates more halogen radical, which then allows propagation to continue. That's why it's a chain. So step 1 is we have some sort of alkane with a hydrogen attached. The halogen strips off the alkane, creating an alkane radical. And that alkane radical can then react with unreacted halogen. And thus it regenerates the halogen radical. Yes, that mono radical on the alkane could react with other alkanes. It doesn't have to react with the halogen. However, if it reacts with another alkane, it's more than likely to pull off a hydrogen-carbon bond. And so it just would be switching one alkane for another alkane radical. And if all the alkanes are the same, that is a non-starter. It doesn't actually do anything. So the idea is that the alkane radical keeps moving until it finds a halide, and then it can be stable, and thus we have the halogen radical. Now, termination can occur when more radicals are present than unreacted hydrocarbons and halogens. So termination is a minor contributor during the propagation stage, but near the end, it's going to be what stops the reaction. And unless you use excess initiator, it won't really happen towards the very end. So when you have a bunch of unreacted halides, a bunch of radical halides, they're going to stabilize themselves. If you get enough carbon radicals, you can form a longer chain hydrocarbon, and of course, eventually you're going to have the halide radical and the alkane radical coming together. So you're going to get a small amount of larger hydrocarbon. Let's see, what's the next slide? Okay, we'll go ahead and stop there. I'm not going to push us too far. I know it's only 20 minutes, but it's not exactly a long chapter. So feel free to start looking at the book, start looking at some of the homework, but we will talk more about this on Wednesday. As I said, I didn't want to push this too far. It's only slide 8. So have a good day. Enjoy your time in the snow.